Hey class, it's Mr. Hofstad with lesson 8 of our third unit, Dynamics. This one is all about inclines. So we did look a little bit at inclines in unit 2, and we're just going to complicate things a little bit. This lesson can be a little bit tricky, and there's kind of one way that I'm going to teach you to do it. There is alternative ways, but I won't go through it. I'm just going to keep everything kind of together, nice and neat, give you these steps that will lead to success in you solving for these problems. So we have something sliding down an incline. Whenever there's this situation, we have a couple of absolute truths. All right, so I'll start by talking about these ideas that were covered in previous videos and lessons. Normal force, right? That's the force between two surfaces, right? Almost like a reaction between the surface pushing back against an object that's sitting on it. It always needs to be perpendicular to the surface, right? So we need to have a 90-degree angle between our normal force and the surface that it is in contact with, right? So that's our first kind of law, you could say, or the first absolute in this situation. Our second one from our last lesson on friction, friction force always needs to be parallel to the surface. So just like normal force needs to be perpendicular, 90 degrees to the surface that the object is sitting on, our friction force needs to be parallel, right? So we need to have it on the same plane in line with our surface, always. So force of friction is always parallel, normal force is always perpendicular, and I guess you could add another point here. The force of gravity is always straight down. Fg, force of gravity, is always straight down. So some people might try to solve these questions without switching our reference system to be lined up with our incline, right? Then force of gravity would be straight down, right? That'll always be true. But it's going to be a lot easier. You're going to be working with a lot fewer trigonometric functions if we actually shift. I like to physically shift the paper that we're working with, right? So force of gravity is still acting straight down relative to the center of the earth, right? It's going straight down, but we're shifting our whole problem, right? It's nice to actually physically turn the page when you're drawing these out so that we're now working with fewer angles. So now the only part that has an angle is our force of gravity, right? And we can break this force of gravity into an x component and a y component, right? Our x component, which is parallel to the surface, and our y component, which is perpendicular to the surface, right? And now we have our new reference system where away from surface, or we could call that up and right, are positive, and down and left are negative. Okay, so we've physically turned our paper and created a new reference system, right? And that is our first step in any inclined problem. We're going to recreate our reference system to simplify our problem, where x-axis, right, our left or right, our horizontal, our x-axis, is parallel to the surface of this incline, and where the y-axis is perpendicular or lined up with our normal force. Sorry, I lost you there. Right, normal force is perpendicular, so we're making that our y-axis. Okay, let's try one of these problems and I'll show you how breaking up this gravitational force into an x and a y, right? So we're kind of we're doing this to match up with our new coordinate system, right? But our x and y components, when you add them together using Pythagoras theorem, will still be the same value as our actual force of gravity, which is directly down when we keep our reference system as we normally would, right? If this weren't an inclined problem, we would say force of gravity is acting down, right? But now we're rotating our reference system, and the force of gravity is broken into two components to be parallel and perpendicular to the surface. All right, so here's an important note. Read questions carefully to see if we have a frictionless surface or not, right? If a question gives you a coefficient of friction, either kinetic or static, right, we're going to have to throw in a new element, right, this force of friction. But sometimes you'll get lucky and a question will tell you that we're working with a frictionless surface, so there's no additional x component. So what we've done here, we've taken our force of gravity, which is straight down, and we've shifted our plane so that we have our y component, FGY, and an x component, FGX. All right, an interesting thing to notice in this geometry of this equation, the angle of the incline after we've rotated our reference system is now always going to be the angle between our original force of gravity and its y component. So we have a hypotenuse, which is our force of gravity. We have an adjacent side, which is our y component of gravity. And we have an opposite side, which is our force of gravity's x component, right? So that was shown in this original one, this original example. We have the same angle between the incline and our gravitational forces components, right? And if you kind of look at the relative size of all of these points, right, this triangle is just a shrunken down version of this bigger triangle, right, where the hypotenuse would be here, right? I'll mark that with just one hash mark. Those are the similar sides, right? And we have an opposite side, right? And then between our hypotenuse and this angle, we have an adjacent side, which would be the bottom of this one. So you can kind of flip and rotate this triangle, then enlarge it, and it becomes this same triangle, right? So we're just doing some simple transformations of a triangle in order to see that we are working with similar triangles with the same angle, both right triangles with this right angle. So we are able to use our SOHCAHTOA. All right, so when we're working with a frictionless surface, we have no force of friction. That is 0. So in our horizontal, after, right, we've rotated so that this is now our x-axis, and this is our y-axis, right? In our horizontal or our x-axis, we have no force of friction. The only force acting in this horizontal or x direction, the only x component of the force is the force of gravity in that x direction, right? And if we solve for f of gx using trigonometry, right, we have the opposite side, so we're going to use opposite over hypotenuse, right? So f gx, where sine of our angle is equal to opposite fgx over hypotenuse just of fg, and we can rearrange to solve for f of gx, right? So the x component of the gravity is equal to the full force of gravity times sine of theta. That's where we're getting this, right? And canceling out our accelerated. So this would be principle of physics 1 or Newton's second law, right? Principle of physics 1. We are rearranging F net is equal to ma to solve for acceleration. And we get the net force divided by mass, or the net force in that x direction, right? We're just talking about our x component, is mg sine theta, force times gravity in the x component, mg sine theta divided by mass. Our masses cancel out, and the acceleration in this x component, or this horizontal direction, is equal to gravity times the sine of this angle of our incline. All right, don't memorize this unless you absolutely need to. Focus on being able to solve for our force of gravity into its x and y components, and recognizing that when we're working with frictionless, the only force acting on the object in our x direction is the x component of gravity. Right, and it doesn't depend on the mass. Whatever mass we have, right, will be accelerating at the same rate. Acceleration will be the same for all masses on this slope. Doesn't matter if I'm a 1 kilogram box or a 70 kilogram man skiing down a mountain. All right, let's try an example. We have a person who is skiing on sheer ice. We've got no friction there. I'm going to draw him as an actual skier. So we know the slope that he's on is 35 degrees. Right? He's sitting here. He's skiing. He's got his ski poles. Sheer ice, no friction, right? But there is still gravity acting down on him. All right? So he is skiing down over a distance of 600 meters. That's going to come in later. We want to determine, so he's going from rest 600 meters, ending up down here. Right, so that distance is 600 meters. He's starting from rest. So this is kind of a kinematic question. So I'm going to list everything that's given. Our initial speed is 0 meters per second. The F we don't know. Acceleration, right? We can break down the force of gravity and find the acceleration that's in the same direction as our displacement, right? So that would be the acceleration in the x direction. He's not accelerating up or down. Okay, so I'm going to, over here, break up his force of gravity, right? So we have our skier. We have force of gravity pulling him straight down. We have our y component, right? Because I've shifted the entire question so that our new x-axis is parallel to the surface. So our reference system would look like this, right? We have our x and our y, where this is positive and this is negative, right? So force of gravity, y is making a 35-degree angle, right? Coming from the angle of the incline, right? This is the same angle used there. And our x component of our gravity, right? So since we're working with a frictionless system, we have no force of friction, right? That's 0. the only horizontal or force acting in the x direction is our x component of gravity, right? So that would be our opposite side. Our hypotenuse would be force of gravity. So we're going to use our sine function. So sine of 35 is equal to our x component, fgx, divided by fg. So solving for that x component, because that's the only force acting in this horizontal direction, fgx is equal to fg sine of 35, right? And we can rearrange, right? Or insert what f of g actually is. It's the mass times gravity sine of 35, right? And coming from our notes, if we're looking for an acceleration in the x direction, right, we're going to need to take that x component divided by the mass. So we have mg sine of 35 divided by the mass. We don't know how much the person weighs, but we don't care because it cancels out. So the acceleration of this guy is equal to gravity's constant, 9.81 meters per second squared. That's very messy. Oh no, what have I done? Gravity, 9.81 meters per second squared times sine 35. Right, so our acceleration is equal to positive because we're going down to the right. So according to the reference system that I created, we're in a positive direction, 5.627 meters per second squared. All right, so I have VI, I have acceleration. I know he's traveling 600 meters. And I want to find out how long it takes. So this is the part of it that I'm not concerned about. Let's get a little more of the whiteboard on here. So I don't care about VF. I'm going to look at my formula sheet and try to find the equation that doesn't have final velocity in it, which is this guy here. So I'm going to use displacement is equal to VIT plus half AT squared. Don't have to use quadratic because this is 0. I'm solving for time. So I'm going to multiply both sides by 2 and divide by acceleration. So I get time squared is equal to 2 times my displacement, which is 600 meters, divided by my acceleration, which I calculated as 5.627 meters per second squared. And I'm going to take the square root to find the time. And I will get 15 seconds. So it takes this guy 15 seconds, regardless of how massive he is, what he weighs, to travel 600 meters down this frictionless slope, right? So whenever we're working with a frictionless slope, we're going to end up with this formula, the acceleration down slope, right? Or parallel to the surface, which is what we're really working with because he's not accelerating up or down from the slope. He's not hitting a sick jump or anything. He's just accelerating down slope at a rate of gravity's constant times the sine of its angle. You can memorize that if you want to fill your mind with more useless information, or you can just solve it from our new reference system and the free body diagram that produces, which I recommend. All right, that is our first example. Let's keep going on with our notes. We have a second example where we are working with friction. Right, so last example of the unit might be a little tricky, but as long as we follow these steps of creating a new reference system, so on and so forth, it should be manageable. So we have the opposite direction incline, because an incline can be in either direction, has a slope of 18 degrees. We have a box that weighs 3.4 kilograms. And we have an external force pulling it up, F. All right, and we know that we are accelerating up the slope at 2.7 meters per second squared. All right, so this is what the question gives us. The rest is up to us, well, other than they give us the fact that coefficient of kinetic friction between the box and this inclined plane surface is 0.515, right? So the bigger this number, the stickier the surface, right? The rougher it is. So we're somewhere kind of in the middle. It's got an average stickiness or roughness. Okay, now we need to add in the rest of our information. So I'm going to look at my box over here and draw in all of the forces acting on it. So we know we have this. Sorry, I'm gonna do something a little tricky and different. I'm going to rotate, right, and then draw in my box. So I'm gonna rotate our reference system. So you can physically rotate your paper, and now you're working off of this, where force of gravity is acting straight down. We have to break it into its components. We have a normal force, right? So I'm going to rotate the reference system so that this box is now parallel with the surface. Hopefully this doesn't confuse you too much, but I've rotated this guy 18 degrees. Now I am parallel with the surface, so my normal force. I'll work in a different color and show you what I'm doing on this other one here. It'll just be a little messier. So force of gravity is acting down, force of friction is acting parallel to the surface. I have this normal force, which I'm rotating my reference system so that it is perpendicular to the surface. I have force of friction, which I have rotated to make parallel to the surface. I have an external applied force, which is what we're looking for in the question. That's our final answer. And I have this force of gravity, right, which I'm going to break into its perpendicular y component and its parallel x component, right? So I've created a perpendicular y component and a parallel x component, which are both at 18 degrees from this downwards, right? So this is what the box looks like, right, on the slope, and I've rotated it so that it's now in my easier to work with incline reference system. All right, so I have a bunch of horizontal and vertical forces. So my new reference system is, we'll say that's right, left, up, down, where up and right are positive, left and down are negative. So I'm going to look at everything in my vertical direction first. Why would I do that? Because I have this troublesome force of friction, which relies on the normal force. Right? So in order to solve for the force of friction, you first need to solve for normal force. Right? So step one, we're going to solve for everything that's perpendicular to slope, which is our new vertical. This is what I've rotated in rotated reference system. Okay, so everything that's happening in my vertical or my Y, my up and down direction, I have, first of all, no acceleration because it's on a surface. It's not bouncing up and down off the surface. Acceleration is equal to 0, so I'm using Newton's first law, uniform motion, where F net is equal to 0. Okay, so I know that my Fn, my normal force, minus, right, in this vertical direction, I've broken up force of gravity into its two components, so I'm no longer concerned with force of gravity. In a straight down direction, I'm looking at its components relative to my new rotated reference system. So that's going to be my FGY, the Y or the vertical component of my force of gravity. And both of those added together equals 0. All right, so I need to solve for this one here, right? So if I add that to both sides, I can find my normal force is equal to my FGY, right? And this guy is the adjacent side of my hypotenuse. So I'm going to use my cosine function, and I'm going to multiply it by f of g to solve for the y component. So I have force of gravity times cosine of my angle is equal to f of gy, where the force of gravity, right, this is just our regular force of gravity, is equal to the mass times gravitational constant times the cosine of my angle, which is 18 degrees. And I can throw in all my values. I get 3.4 kilograms, 9.81 meters per second squared, and cosine of 18 will give me 31.72 newtons. 31.72. All right, so for there to be 0 acceleration in the perpendicular or vertical direction, we need the normal force to equal 31.72 newtons. All right, our second step is going to be parallel to slope. This is now our horizontal, or our x. So in the parallel direction, we actually are accelerating at 2.7 meters per second. So we're working with principle of physics 1. F net is equal to mass times acceleration. So I have the mass, I have the acceleration, right? Now I'm able to solve for that net force. All right, so this net force is equal to the mass, 3.4 kilograms, times our acceleration in this horizontal direction, right? Parallel to the surface, we're going 2.7 meters per second squared. That's given right in our question in the diagram. Really important to read those diagrams carefully. So we have mass and acceleration, and the net force we can break into its components that are in this parallel plane. So we have the applied force and the force of friction. So the applied force would be positive, and our force of friction would be negative. And it'll all equal this mass times acceleration. I'm just going to leave those as variables until the last step so I don't have to carry it through the whole way. All right, so in order to solve for F, this is what I'm looking for. I'm adding force of friction to both sides. We have this is equal to our force of friction plus our mass times our acceleration. We need to solve for the force of friction. All right, force of friction will always be equal to the normal force times our coefficient of friction. Force of friction is equal to Fn. Since we're moving, we're going to be using our kinetic. Also, it's the only one that is given to us. Sorry, I lost you for a minute. Okay, so we're solving for the force of friction, which is dependent on the normal force, which we calculated here, right? Using our vertical components and our coefficient of kinetic friction. So we solved for this, we're given this, we have 31.72 newtons times 0.515. Force of friction is equal to, sorry, I'm just going to throw this all together. And I forgot about one component here. We also have this. This is probably the biggest error everyone will make. I almost forgot about it, so pay close attention to your horizontal components, not forgetting about the x component, right? So this is actually negative f of gx plus that applied force minus force of friction, right? So we have to add force of gravity's x component onto that side when we're solving for force as well. All right, so this force of friction, I'll calculate 31.72 times 0.515 is equal to 16.33. We also need to solve for f of gx, so that'll be our opposite. So we're going to use the sine function. Okay, so I'm going to throw in everything I know. We have force of friction as 16.3. We have our mass and our acceleration, 3.4, 2.7. And we have force of gravity in the x direction, which is going to be our Fg times the sine of 18, because it's our opposite. So we're going to have our mass again, 9.81 gravity. So this is our Fg, and then multiplied by sine of 18. All right, adding all of those together, that force that's applied in order for it to accelerate at 2.7 meters per second squared needs to be 16.34 plus our mass times our acceleration plus our x component of gravity, which is the sine, right, of the gravity, because it's our opposite side related to our hypotenuse, which is the only one we can calculate using the mass and gravitational constant. Mass, gravitational constant, x component, horizontal component is the sine of that times 18. Add all three of those values together, because that and our net mass and acceleration are all in that direction, we get 35.8 newtons. That is a tricky one, and it's not super neat and organized. Probably should have used 2 whiteboards. Hopefully you can follow along. The trickiest part of those types of questions is when you're looking at the parallel, adding all of these x components of our force, we need to remember about gravity, right? It's easy to remember gravity when we're working in our y component because we need it to solve for the normal force. Super easy to forget about it here. So make some really visible notes to yourself that you're not going to forget this x component when we're looking at our horizontal forces, right? There's still a component of gravity. Once we've rotated our effort system, that's acting horizontal, right, parallel to our slope. And that is essential for us in determining the net force that is parallel to the slope, right? This guy here. He depends on friction, which will be opposing, and the gravity, which will usually be, actually it'll always be opposing unless you're accelerating down the slope. All right, good luck. Let me know if you have any questions. As usual, I'm sorry for the tight working space and the mess, but please don't forget me